Hi everyone. Several people recently asked me if there was going to be a video for the practice final exam, and I hadn't originally thought I was going to do it, but since a number of people asked, I did decide that it would be a good idea. So in this video, I'm going to go over these questions. I will be honest, some of them I'm going to go over relatively quickly, but I figure something is better than nothing. And then if you look in the description below, you can find a copy of the problem set. You can also find a copy of the answers, the one that I'm going to write on here. I'm just going to scan it when I'm done. And then finally, you can find a list of the questions and the time. So if there's a specific question you want to watch, just scroll down to the description, find that question, click on the time, and it will just automatically get you to that time, so you don't have to watch through the whole video or try to find where each question is. So that is basically that. I hope that you find this useful, and I'm going to go ahead and get started now with question 1. I didn't mean to do that. So for this one, the first three questions are related, and we're given the reaction of p-aminophenol with acetic anhydride to form acetaminophen, which is a common pain reliever in Tylenol. And basically, we want to figure out the theoretical yield, the percentage yield, and the limiting reagent. So we're given that we're going to use 5 grams of p-aminophenol and 3 milliliters of acetic anhydride, and we want to know how much acetaminophen we can make using that. And basically, I'm going to go through all these three questions at once because there's no sense in doing them one at a time. So let's go ahead and do this. So first, what we want to do is we want to figure out how much acetaminophen we can make with all of our p-aminophenol. Then we want to figure out how much we can make with all of our acetic anhydride. And whichever one of those is less, well, that's how much acetaminophen we're going to be able to make, because we're going to run out of it, because we're going to figure out how much we can make with all of it. So obviously when we've used all of it, there's none left. So there's not a lot of space here, so I'm going to kind of try to cram this in. And it's going to look a little awkward, but it's, it'll fit. So let's do this. So I'm going to call this p-amino, just so I don't have to write p-aminophenol all the time. I'm going to call this AA, acetic anhydride, and I'm going to call this ACE for acetaminophen. So just abbreviations so that it's, I don't have to write those words out every time. So what I want to do here is I want to go from grams of p-aminophenol to moles of p-aminophenol to moles of acetaminophen, what I'm trying to figure out, to moles, grams of acetaminophen. So this is my plan of attack to figure out how much acetaminophen I can make if I use all of my p-aminophenol. So starting in this case with 5 grams of p-aminophenol times, I'm given the molar mass right here, so it's 1 mole of p-aminophenol is equal to 109.1 grams of p-aminophenol. And I want that on the bottom so the grams cancel out. Now I need to convert it from moles of one thing to moles of another. Now you may remember from general chemistry, we always use the balanced chemical equation to go from moles of one thing to moles of another. In organic, we have these organic molecules, but that doesn't really matter. At the end of the day, for every one of these I react, I get one of these. So there's 1 mole of p-aminophenol gives me 1 mole of acetaminophen. And again, I put this on the bottom so it'll cancel out. Now I want to convert to grams of acetaminophen. Well, I'm given the molar mass. This time I want moles on the bottom so it'll cancel out. 1 mole of acetaminophen on the bottom, and on top I want to put the 151.2 grams of acetaminophen. And when you do all that math, you get 6.9 grams of acetaminophen. So what this means is that if I react all 5 grams of p-aminophenol, I can theoretically make 6.9 grams of acetaminophen. Now I need to figure out what happens if I react all of my acetic anhydride. And what I'm going to do for the acetic anhydride is I'm going to put the plan of attack here, and I'm going to put the dimensional analysis here. I know it's not pretty, but it'll fit on the page that way. So in this case, I want to do the exact same thing. I want to go from grams of acetic anhydride, but you'll notice here I'm given milliliters. So I first have to use the density to convert that to grams. So I actually want to go from milliliters of acetic anhydride to grams of acetic anhydride. Once I have grams of acetic anhydride, I can find moles of acetic anhydride using the molar mass, then moles of acetaminophen using the balanced chemical equation, and then grams of acetaminophen using the molar mass of acetaminophen. So it's one extra step because I have to go from milliliters to grams. So as I said before, I'm going to write it down here because there's space down there. So if we look here, I have 3.0 milliliters of acetic anhydride times. Now I want to put the density, I want to use the density to find the number of grams. Well, this is 1.08 grams per 1 milliliter. I want milliliters to cancel out, so I put the 1 milliliter of acetic anhydride on the bottom and the 1.08 grams of acetic anhydride on the top. Next, I want to convert it to moles. To do that, I need to use the molar mass. So I want to use the 102.1 grams of, in this case, acetic anhydride, which is 1 mole of acetic anhydride. Now I want to convert it to moles of acetaminophen using the balanced chemical equation. 1 acetic anhydride gives me 1 acetaminophen. So I want to put 1 mole of acetic anhydride on the bottom and 1 mole of acetaminophen on top. Then finally, I want to convert from moles of acetaminophen to grams of acetaminophen, which is exactly what I did before. So since I'm doing the same conversion, I can use the same conversion factor. 1 mole of acetaminophen on the bottom and 151.2 grams of acetaminophen on the top. Multiplied by the top, divided by the bottom, multiplied by the top, divided by the bottom, repeat until the end. And when you do all this math, you get 4.8 grams of acetaminophen. So if I use all of my p-aminophenol, I'll make 6.9 grams of acetaminophen. If I use all of my acetic anhydride, I'll make 4.8 grams of acetaminophen, which is less. Well, since I can only make 4.8 grams of acetaminophen with all of my acetic anhydride, I will run out after I make 4.8 grams of acetaminophen. Therefore, I can't possibly make any more. That makes this the theoretical yield. And it makes acetic anhydride the limiting reagent. So, to answer number 1, what is the limiting reagent? The answer is acetic anhydride. To answer number 2, what is the theoretical yield? The answer is 4.8 grams. Note that they're related to each other, but they're not exactly the same thing. One is a chemical and one is a mass. Finally, it says if the actual yield of acetaminophen in question 1 was 4 grams, what is the percent yield? Well, percent yield is equal to the actual yield divided by the theoretical times 100, because it's a percentage. So in this case, I want to take the actual yield, which is given in the problem. In the lab, you would measure this on a balance, but here it's given in the problem. 4 grams divided by the theoretical yield, which is 4.8 grams times 100. And when you do all that math, you get 83.3333, but it's 2 sig figs, so 83%. So the percent yield is 83%. So here we have limiting reagent, theoretical yield, and percentage yield in 3 separate questions, but they're all related to each other. Question 4 says, which of the following are uses of TLC? You'll recall that TLC involves using a thin plate, and we could spot some analytes on it, and then we put it in a beaker and we elute solvent through it. And maybe this one has a spot here and a spot here, and maybe this one is exactly the same. So you could have different spots on these, or maybe they're different or whatever. So TLC can definitely be used to separate components of a mixture. That's absolutely true. You can use it to identify an unknown, because if the spots travel the same distance and there's a good likelihood that that compound is in the unknown, then you could use it to identify a known. You could use it to monitor reaction progress. If, for example, this is the starting material and this is the product, your reaction mixture would have both starting material and product in it, so you know the reaction wasn't complete. Or if it had just product in it, you know it was. Or if it had just starting material in it, you would know that it hasn't even started. So this, answer question number 4, is all of the above. These are all uses of TLC. Question number 5 says, a student runs a TLC and the sample spot moves 2.1 centimeters while the solvent front moves 6.2 centimeters. What is the RF? Well, if you remember, RF is equal to the sample distance, I'm just going to write it as sample, divided by the solvent front distance, I'm just going to write it as solvent. So in this case, it's 2.1 centimeters divided by 6.2 centimeters. And when you do that math, you get 0.34. Note that the RF must always be between 0 and 1, right? It could move the same distance as the solvent. It's not possible for it to move further than the solvent did. And it could move 0. It could not move at all. So in this case, the answer is 0.34. But I will point out there's two answers here that don't make any sense. So basically it's the sample divided by the solvent, which in this case is 0.34. Question 6 says, in an experiment that uses TLC, like the one performed in this course, which of the following statements is true? So in our course, we used a TLC plate with polar silica gel, and we spotted our samples on it, and then we eluted it with a non-polar solvent. So polar solutes that were spotted onto the plate would have a strong affinity for the silica gel, and therefore they wouldn't move very far with the relatively non-polar solvent. And non-polar solutes would have a weak affinity for the silica gel, and therefore they would move relatively far with the non-polar solvent. So that's essentially what we did. So in this case it says the mobile phase is relatively non-polar organic solvent or a mixture of solvents. That is absolutely true. So that's good. The stationary phase is polar silica gel. That is absolutely true. That's what we did. Polar compounds have small RFs because they have a strong affinity for the silica gel. The silica gel is polar. So if the compound is polar, it'll stick to the silica gel and it won't move very far. If it doesn't move very far, it has a small RF. If you're not sure how to calculate RF, please go back to question 5 where we go over that. So all of these pieces of information are true in question number 6. Question 7. Question 7 says, in an experiment that uses column chromatography like the one performed in this course, which of the following statements are true? So column chromatography is like upside down TLC that we just talked about in question 6. So if you haven't seen questions 5 or 6, you might want to view those first. So basically what we have is we have a column like this, and that column is filled with polar silica gel. And then we put some solvent on top of it, and that solvent is relatively nonpolar. So if the compounds that we put on the top of the column are polar, they stick to the silica gel and they elute very slowly. If the compounds that we put on the top of the gel are less polar, then they have a weaker affinity for the polar silica gel and they elute more quickly. So I'm going over this relatively quickly, but I did want to go over it like better than none. So that's basically that. In an experiment, let me read it one more time. In an experiment that uses column chromatography, like the one performed in this course, which of the following statements are true? Polar compounds elute slowly and have longer retention times because they have a strong affinity for the silica gel. That is absolutely true. Polar compounds stick to the silica gel and they come out more slowly. Remember that this is working from the top down, so they're coming out down here at the bottom of the column. The stationary phase is polar silica gel. That's what we did in this course. The mobile phase is a relatively non-polar organic solvent. That's what we did in this course. I think we used toluene and then we doped it with ethyl acetate. Toluene is methylbenzene, so it's just carbon and hydrogen, and it's relatively non-polar. So all of these above statements are true, which is the correct answer for number 7. Number 8 says, how many hydrogens are on the molecule below? So these represent carbons, of course, which I'm drawing in here. And we'll remember that carbon always has 4 bonds. So this carbon has 1 bond, so it must have 3 bonds to hydrogen. This one has 2 bonds, 1 carbon, 2 carbon, so it must have 2 bonds to hydrogen. This one has 2 bonds, so it must have 2 bonds to hydrogen. This one has 3, carbon, bromine, and carbon, so it must have 1 bond to hydrogen, and this carbon has 1, so it must have 3 bonds to hydrogen. 1, 2, let me count them in a logical way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That makes 11 total hydrogens on that molecule. Number 9 says, what is the functional group of the molecule below? Well, we have C double bond O, CH3, and there's a CH3 here also. This is an ester. C double bond O bond OR is an ester. This is actually methyl acetate. A carboxylic acid is R bond C double bond O bond OH. And amine is R bond C, I guess. Or we could just do R bond N, bond R prime, bond R prime prime, or these could be H's, or these could be carbon-containing groups, depending on if it's primary, secondary, or tertiary, but one of these groups has to be a carbon. And a ketone, I think that's spelled incorrectly, I think that it shouldn't be there, is R bond C double bond O bond R prime. So this one is an ester. Question number 10 says, what formal charges are present in the molecule HCOO? Assume that all other atoms other than hydrogen have an octet. C is the only central atom. So we put C in the middle, we bond it to an H and two O's, and what you're going to find is that you're going to have a double bond O here with two lone pairs, and you're going to have three lone pairs on this, making it minus. So when you look at this, carbon has a neutral formal charge because it wants to have 4 electrons around it, and this one has 1, 2, 3, 4. You count the bonds as 1 each because there's 2 electrons. One belongs to hydrogen, one belongs to carbon. So we just for formal charge count them as 1 each. This oxygen is minus because oxygen wants to have 6 electrons around it, and this oxygen has 1, 2, 3, 4, 5, 6, 7. It's got an extra electron, so it's negatively charged. And this oxygen wants 6 around it, has 1, 2, 3, 4, 5, 6. So it is neutral. So in this case, 1 oxygen is -1, and carbon is 0. So that is choice letter B for question number 10. Question number 11 says, which of the following compounds has the lowest boiling point? And the first one is 2,2-dimethylbutane. So 1, 2, 3, 4 carbons, and it's a dimethyl like that. The next one is 3-methylpentane. 1, 2, 3, 4, 5 carbons, and a methyl like that. Next is hexane, which is just 1, 2, 3, 4, 5, 6 carbons. And the last one is 2-methylpentane, which I realize this is 2-methylpentane, and it should be 3-methylpentane. So 2-methylpentane is 5 carbons. And, I did it backwards again, and the methyl group is there. So let me redraw these because I screwed up. So 3-methylpentane is 5 carbons with a methyl there, and 2-methylpentane is 5 carbons with a methyl there. Which of these has the lowest boiling point? Well, they're all isomers because they all contain 6 carbons. But in this case, this molecule is the most compact, so therefore it's going to have the lowest boiling point. This molecule is the most spread out, therefore it's going to have the highest boiling point. These two are close, so we wouldn't ask you to compare these two, but compared from this one, and comparing this one to all 3 of the other ones, this is the lowest boiling point, and hexane would be the highest boiling point. All right, it says, which of the following are strong acids? This is just basically something you need to memorize. The strong acids that we use in this class mostly are HCl and H2SO4. So these are the strong acids that we use. For this question, HCl is the only one that's a strong acid. Sodium bicarbonate is baking soda, it's a weak base. Sodium hydroxide is sodium hydroxide, and it is a strong base. So this, to question 12, the answer is A. 13, it says, which of the following indicate a pure sample? A narrow melting point range and a melting point near the accepted value both indicate a pure sample. These are the 2 things that indicate a pure sample. A broad melting point range and a low melting point, lower than expected, melting point. These 2 things indicate an impure sample. So pure is narrow melting point range and a melting point near the accepted value, which makes the answer to this question A and B. And impure is a broad melting point range and a lower than expected melting point. So that's just something you should basically memorize. Question 14 says, what conditions must be met for a successful liquid-liquid extraction? The two solvents have to have different densities. Yes, one solvent has to float to the top. So if they don't have different densities, that becomes difficult. So they do have to have different densities. The solute is preferentially soluble in one of the two solvents. Yes, the solvent needs to dissolve in one of the things and not in the other. If the solvent doesn't dissolve in either solvent, a liquid-liquid extraction will not work. If it dissolves in both solvents, a liquid-liquid extraction will not work. So it has to be soluble in one and not in the other. The two solvents are immiscible. Of course, if you take water and acetone and you try to do a liquid-liquid extraction, you're only going to get one layer. You're not going to get two layers, so that's not going to help you. So in this case, all of the above information is required in order to have a successful liquid-liquid extraction. Question number 15 says, gas chromatography, like what was performed in the lab, works best with which mixture below? Well, gas chromatography separates compounds based on their boiling point, and there's two basic properties that have to be met in order for gas chromatography to be successful. First of all, the compounds have to be volatile, which means they have to go into the gas phase. So if you see things like sodium sulfate or NaCl, these things are ionic. Ionic compounds are not volatile, so therefore they're not going to work. So these are not good choices. The other thing is the compounds are actually burned at the end of the detector. You don't need to know that to solve this problem, but you can't detect water very well on a gas chromatography like the one we have in lab, because it uses a flame ionization detector, which involves burning the compound. Water isn't flammable, as you know, so it doesn't get detected very well with an FID, or flame ionization detector. But organic compounds like hexane and pentane, which have different boiling points and are flammable, those are the kinds of things that you want to separate with GC, not ionic things. So that is basically how we solve question 15. Whoops. Sorry about that. All right, question 16 says, consider the ranked polarity of all fictitious compounds with different functional groups is A is greater than B, C, D, in that order. With A being the most polar, so this is the most polar on this side, and this is the least polar on this side. So A is the most polar, D is the least polar. Which compound will elute down a silica gel column the slowest? So as we talked about in a previous question, I can't remember which one right now, we have a column packed with silica gel, and then we put toluene, because that's what it says we used, it's the yellow one on the top. Silica gel is polar. So which one of these compounds will stick to the silica gel the most is the one that will elute the slowest. Well, the most polar compound is going to stick to the polar silica gel the most, and therefore it will elute the slowest. The least polar compound will stick to the silica gel the least and should elute the fastest. Question 17 is very similar to a previous one we did where we were asked about the boiling point of these compounds. It says, which of the following compounds will have the lowest retention time when separated in a GC? The lowest retention time in a GC, which mostly separates by boiling point, is also the lowest boiling point. So which one of these has the lowest boiling point? Well, this looks like this. That one looks like that. That one looks like that, and that one looks like that. The one with the lowest boiling point is going to be the one that's the most compact. So since this has the lowest boiling point, it's going to elute through the column fastest. Furthermore, hexane, which has the highest boiling point because it's the most spread out, notice that these are isomers, just like the previous question with these exact same molecules. They all have 6 carbons and the same number of hydrogens, 14. So these are all isomers. So the most compact one has the lowest boiling point, the most spread out one has the highest boiling point, or has higher dispersion forces, however you want to think about it. So therefore, 2,2-dimethylbutane will come out of the column first. So number 18 says, GC primarily separates mixtures based on their, and then if you watch question 17, we already talked about this, but GC, where the oven gets hot, and elutes column through there, or elutes compounds through a column, mainly separates compounds based on their boiling point. Low boiling point compounds come out first, high boiling compounds come out last, but the separation is based on boiling point for question 18. Question 19 says, the two molecules below are dissolved in ether and placed in a separatory funnel. Is 10% NaHCO3 a good solution to separate these two molecules? So there's a lot of stuff going on in this question that we need to think about. First of all, we have ether and we have 10% NaHCO3. The other 90% of this is water. So this is an aqueous solvent. So we will get 2 layers. 2 layers is good. Maybe it'll work for liquid-liquid extraction because we are going to get 2 layers. We have immiscible solvents. Now what we need to look at is the 2 molecules. Well, sodium bicarbonate is a base. Bases take protons. And what's going to happen is it's going to take this proton off and you're going to get minus Na plus essentially. And this molecule is ionic. Ionic molecules will be aqueous. Let's look at the functional group on this one. We again have a carboxylic acid. We again have an acidic proton. That's going to come off and we're going to get Na plus. And this is again going to be aqueous. So is this an effective method of separating these 2 molecules? No, because look, this one's aqueous and this one's aqueous after we add the sodium bicarbonate. So no, both molecules will be in the aqueous layer. This is not effective. Sodium bicarbonate is good if one of these molecules is neutral or one of these molecules is a base. However, if they're both acids, we're not going to separate them. Question 20 says, the 2 molecules below are dissolved in ether and placed in a separatory funnel. Is 5% HCl a good solution to separate the 2 molecules? Well, let's take a look. If this is 5% HCl, it's 95% water. So we're going to have an aqueous layer and an ether layer. Both of these molecules are originally dissolved in ether. But what's going to happen if we add HCl? Well, HCl is an inorganic acid which reacts with organic bases. You may recall that organic bases are amines. So if we look at this molecule, it has an amine functional group. If we look at this molecule, it's neutral. It's not going to react with the acid at all, and this is going to stay dissolved in ether. But this molecule is a base, so it has a lone pair here, and it will accept, I'm trying to cover up that lone pair, a proton. That'll put it give it a positive charge on N, and we'll have a Cl minus just as a counter ion. This is ionic. Ionic compounds are not soluble in ether, but they are soluble in water, so this will be aqueous. This molecule will not dissolve in the 5% HCl, or the water for that matter. It's mostly the water as a solvent. So this molecule remains in ether because it's neutral. Well, we have one in the aqueous layer and one in the ether layer. We have separated them. And here it says, yes, molecule A will be in the aqueous layer, so that is our best choice. Question number 21 says, when an organic amine is dissolved in ether, when an organic amine that is dissolved in ether is exposed to 5% aqueous HCl in a separatory funnel, and the funnel is shaken, what phase will the amine be in? This is exactly the same question as number 20. So here we have R bond NH2. And we have this dissolved in ether. And we add HCl dissolved in water, aqueous. What happens? The amine gets the proton. And what you end up with is R bond NH3 was 2, now it's 3 with a plus charge. And then the counter ion is Cl minus. This compound is ionic. Ionic compounds are not soluble in ether, but they are soluble in water. So this one's aqueous. So the answer to this question, number 21, is aqueous. And if you didn't see number 20, it's basically the same question. Number 22 says, if the compound below is dissolved in water, what would be done to recover the compound? Well, we have a deprotonated carboxylic acid, right? This is a carboxylic acid if it had an H here. But this now is an ionic salt, and it's dissolved in water, so it's aqueous. If we want to reform the carboxylic acid, we want to add something like HCl, aqueous. What's going to happen? This proton is going to go onto this molecule, and we're going to reprotonate the carboxylic acid. This carboxylic acid has 8 carbons, right? 6, 7, 8 carbons. So it's large carboxylic acid. This is not going to be soluble in water. So this is going to precipitate out as a solid. So if you want to recover an organic compound that's ionic from the aqueous layer, turn it back into the organic compound by adding acid, and it should precipitate out of solution as shown here. Question 23 says, if a mixture of compounds below is distilled, which compound will be collected first? So in a distillation, we essentially have a distilling flask on this side, I can't draw well, a distillation head, something like this, a condenser, like this, and then usually you have some kind of vacuum adapter thing here, and then a receiving flask over here. So the molecule that's going to make it to the top and be condensed and drip over to the other side is the one with the lowest boiling point. Now, I don't remember the exact question numbers, but we looked at these compounds several times to find which is the least boiling point. They all have 6 carbons and 14 hydrogens. Hexane looks like this. 3-methylpentane looks like this. 2-methylpentane looks like this. And 2,2-dimethylbutane looks like this. Since this molecule is the most compact, it has the lowest boiling point. If it has the lowest boiling point, it's going to be the most likely to reach the top of the condenser first and drip into the receiving flask. So the compound that will be collected first is this one, and the compound that will be collected last is this one. Now, you may be wondering, well, do these compounds have a different enough boiling point in order to do simple distillation? And the answer to that is probably not. You would probably need a very advanced fractionating column in order to actually separate these types of molecules because they're so close. However, in theory, the molecule that would come out first is 2,2-dimethylbutane. Question 24 says, which of the following is the conjugate acid of CH3NH2, which is methylamine? So we need to find the conjugate acid. If you want to find the conjugate acid, this has to act as a base. What do bases do? Bases accept protons. Well, where's the place that's going to accept the proton? That's on nitrogen. So what you're going to end up with is CH3NH3. We add a proton to nitrogen. When you add the proton to nitrogen, that has a positive charge. Now, because of the typing, the positive can't be shown very well on the nitrogen, but the overall charge is plus. So this is the answer to our question, choice letter A. Question 25 says, acetone is a, well, acetone is CH3, C double bond O, CH3. It's a ketone with a methyl group on both sides. This is a common organic solvent used to clean glassware regularly. An organic compound having 3 carbons, yes. A ketone, yeah, it's got a ketone functional group, so it is all of the above. It's important that we know something about the common organic solvents that we use in the lab. Question 26 says, what is the functional group of the compound below? We have a carbon group, an oxygen in the middle, and another carbon group. So this is RO, R prime, this is an ether. In fact, this is diethyl ether, because this is an ethyl group and this is an ethyl group, or just commonly called ether. This is the stuff you use several times for liquid-liquid extractions. So again, just like question 25, it's important that we know something about the common solvents that we use in this course. Question 27 says, which of the following compounds is a drying agent commonly used in the lab? Well, the common drying agent that we use in this lab is sodium sulfate, Na2SO4. Sulfuric acid is an acid, sodium hydroxide is a base, and sodium bicarbonate is a weak base. The drying agent that we use is sodium sulfate. Number 28 says, what type of carbocation is the most stable? And we have primary, secondary, tertiary, or quaternary. Well, if we look at carbocation stability, the more carbons you have attached, the more stable it is. So in a primary carbocation, we have a carbon bonded to possibly another carbon or no carbons, with a plus charge. So this carbon back donates electron density to this carbon, so it helps to stabilize it, but there's only one carbon, so it's not very stable. In a secondary case, we have two carbons back donating to the plus charge, which is more stable. In a tertiary case, we have three carbons back donating, which is the most stable. In a quaternary case, it's not going to be a carbocation, because if it's bonded to four other carbons, it's not going to be plus charge. It's going to be neutral. So the answer here is the tertiary carbocation, because the more you have back donation of these carbon bonds, then the more stabilized the carbocation is. These are donating electron density, which stabilizes positive charges. Number 29 says, when HBr is added to an alkene, which of the following statements are true? So we have C, double bond C, and there's some stuff sticking off of it, and we have HBr, just like we did in the lab. Well, what happens is this grabs this, and what you end up with is C, bond H, and this one has a positive charge, and the one that's going to have the more stable positive charge is the one that's supposed to form more. That's not the point of this question. So in this case, what happens is these electrons attack this positive charge. Well, the H is a positive charge, it's like a nucleus. So the pi bond of the alkene acts as a nucleophile. It doesn't act as an electrophile. It doesn't attack electron density. It doesn't attack the bromine. It attacks the H. The H plus acts as a nucleophile. No, the H plus acts as the electrophile. It goes for the electron density, and bromide doesn't really do anything here, so that's not the answer. So this is basically what's going on, and this isn't drawn out perfectly because we don't show everything else that's on here, but hopefully you get the general idea. Number 30 says, students need to be familiar with acid-base extraction for the final exam. That is true, and we went over several questions of acid-base extraction. Number 31, students need to memorize the amounts of every reagent added to an experiment throughout the semester. That is false. Please use this as a guideline for this being this practice test, as a guideline for what's on the final. It's mostly about the why. We're not going to ask you how much ether did you add to the separatory funnel in step 3 of experiment 4, whatever. We're not going to ask you stuff like that. So don't memorize the experimental details. Understand the why. Why do we add different things? Number 32 is, students need to be familiar with the factors or trends that affect the boiling point of compounds. We went over several examples of this in the practice test, and you definitely need to know that. So if you have nonpolar compounds, it's going to be based on the size of the compound. The bigger the size, the higher the boiling point, or the spread out nature of the compound. So hexane, which is a 6-carbon chain, has a higher boiling point than 2,2-dimethylbutane, even though they have their isomers, they have the same number of carbons. This is more compact, lower boiling point. This is more spread out, higher boiling point. However, if we were to compare something like pentane with something like 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons, so something like nonane, this one is going to have a higher boiling point, and among these two, this one's going to have a higher boiling point because it is more spread out. So that is basically how boiling point works. Number 32, students need to be familiar with the mechanism of the addition of a haloacid to an alkene for the final exam. And that is absolutely true. And if you go to question number 29, 29 is getting at this mechanism. So make sure that you review that question. Question 34 says, the following 2 molecules are what type of isomers? Well, let's see if they're even isomers. So first, we look at this carbon, and it's bonded to an ethyl group, a methyl group, a chlorine, and a hydrogen. And this one, same thing, an ethyl group, a methyl group, a chlorine, and in this case, a hydrogen that way. So these are chiral. This is a chiral center. Second thing is, they're both 2-chlorobutane, something 2-chlorobutane. So the chlorine is on the same carbon. If in one case it was on carbon 1, in the other case it was on carbon 2, they're just different molecules. If you notice here, we've switched two groups. We switched the chlorine and the hydrogen. If you switch two groups on a structure like this, they have to be enantiomers. First of all, you have to figure out if they're chiral, because if they're not chiral, they might be the same molecule. But these are chiral molecules, because this carbon is bonded to 4 different things, and it's switched. We switched chlorine and hydrogen. If you switch them, you definitely make the opposite enantiomer. So these are enantiomers. So that is the practice final exam. I hope that you've found this helpful, and I wish you all good luck on the final exam. Thank you for taking the time to watch this video.